So now that we've looked at the finite difference equations themselves, we're going to talk about how we can solve these finite difference equations. The basis is we start with deriving the equations for all the cells, and we end up with an equation that looks something like this. So we have a coefficient for each temperature and a value for each temperature, and then we have a source term based on the heat generation rate. And we can rewrite the equation, and it gives us something that looks like this. So we convert this into a matrix form. And here we have basically something that's equivalent to AX plus B, where B is the source term, T is the solution, and A is a square matrix. The most straightforward method for solving this comes from linear algebra, where we just invert the matrix A and we can solve for temperature. There are some requirements here. We can use, for instance, Gauss-Jordan elimination or row reduction, but matrix A has to be invertible. It has to have an inverse. And this is okay for small problems. However, in general, it requires the number of equations cubed operations to solve this matrix. So this can be done by a computer for problems with several thousand cells or so. We actually can write a script in something like MATLAB where we can compute this. However, if we have a large number of cells, millions of cells, this isn't practical because it requires too many operations, it takes too long, and uses too much RAM. For most problems, this type of direct inversion solution is not realistic. So for larger problems, we typically use iterative solutions. They're often much more efficient than direct solutions. We start with some initial guess, and then we solve each equation in sequence, and then we continue cycling through the equations until we reach what we call convergence. Convergence is kind of a fuzzy concept, but it just means that we've reached a solution where with each iteration, the change in our solution is small. So the convergence criteria can be either some number of iterations, or the residual, or the change in a certain value, becomes smaller than some number. Now the two simplest methods, there's many methods. Two simple ones are Gaussian iteration and Gauss-Seidel iteration. Gaussian iteration basically uses the previous guess for all of the possible temperatures to solve for new temperatures and updates them all at once. Gauss-Seidel iteration is faster. In Gauss-Seidel iteration, you update each equation as you go, and that helps speed up convergence because you're using the new values sooner. So in Gauss-Seidel, we write equations explicitly for the temperature at the node we're interested in. So don't worry too much about all of the detailed math and what all the subscripts mean. We're just taking the finite difference equations we had from our previous presentation, and we're solving those equations for Tmn or Tij. So we start with our initial guesses for all the temperatures. We use a for loop or something like that to update each value in the solution, and then we check for convergence. And we replace the old value with the new value as soon as it's calculated. And we can repeat that if we need to. So we can actually show an example of this in MATLAB. So here in the MATLAB code, we have the for loop for all of our values, and then we calculate the new value, we determine the residual or the change in the value, and then we update the original matrix with the new value right away. And then we repeat until the residual is smaller than some very, very small value. Now, it's important to note that when we're using these numerical methods, a converged solution may not necessarily be very accurate. You can see from the graph here that the converged solution after six iterations doesn't look much like the exact solutions. There's a lot of error. The reason for that is because we have a very large cell size. So we have to be aware of mesh errors and algorithm errors, and we have to look for what's called grid independence. Grid independence just means that the solution no longer changes as you change the number of cell sizes, or the number of cells. Now, it's good engineering practice to always verify your solution by just looking at an overall energy balance. So does the energy in, energy out, energy generated, and energy stored all add up to zero? Remember that CFD and other numerical models are still mathematical models. They're no better than the equations you base the code on. You can have convergence error, mesh error, and so on. So just because you get a solution doesn't mean you have the right solution. So we always want to verify with experimental data or compare with simplified models and control volume balances to see if our solution makes sense.